Hello, hello. Today we're going to talk about lid-driven cavity flow, and this is considered a canonical problem, meaning it forms the canon of fluid mechanics. It's a classic problem. All right, so we're going to work through this lid-driven cavity flow problem. And we're going to solve this using the MacCormack method. And so we're going to go over that. We're going to just look at a stencil briefly and focus on the boundary conditions, and then for this particular problem, and then I'll show you some solutions to that. So this is cavity flow. This is the far field flow here, and in this case, there's a cavity here with a base and a height, and the fluid is in there. And you can see that because of this free stream velocity flowing over the top of that cavity, it induces a circulation within that cavity. And so as we change the base and the height, we can see some different things, like if it's really, really tall, if h is large compared to b, so b over h is 0.5, then you can actually have kind of a stagnation region below this recirculation zone. And as h gets smaller relative to b, that goes away. And then as it gets even shorter, h with respect to b, you can have a phenomenon known as recirculation, or secondary flow appear. So you have secondary cavities being driven within the main cavity. So really interesting phenomena. All right, so here's the problem that we're going to look at. It's a box, a rigid box. It's planar. The box in this case is d by d, so it's the same size on both sides. And then on the top, we've got a moving plate. So everywhere we're going to enforce the no-slip boundary condition, where the three sides here are not moving and the top is moving. I found a quick little video on YouTube. I'll show it to you here.
In lid-driven cavity flow, the top surface of a fluid-filled box is driven at constant linear velocity, while the other 5 surfaces are kept still. In this video, you can see the transient behavior of the system once the lid is actuated. Notice that flow proceeds along the top surface and then impacts the right wall, creating a downward turbulent jet that eventually recirculates with the driving lid. In the last fast-forwarded clip, notice that the center is very circular, with regions of turbulence at the corners. Also note that, although the top is slightly dimmer, this is only due to lighting constraints.
So it is as you would expect. It just goes in a circle there. The problem with this video compared to what we're going to do is that this is a turbulent flow, and so you can see there's a lot of motion in there. That's great. And you can't see the recirculation zones if they appear within this turbulent flow, but it's just to give you an idea of what it looks like and so forth. All right, so in order to solve this using a CFD solution, we're going to need a computational domain. So I'm going to use just the ij indices, and we're going to lay the domain in there like that. And then I'm going to assume that you can have any number of ij's. In this case, this is a 64 by 64 mesh size domain. And it's zero relative because I'm using fortran, meaning I can't have 0 indices at the lower boundaries. So it's really 65 total nodes in there per dimension. All right, so as before, as always, you've got these central difference nodes, and then you have the nodes on the boundary. Not necessarily central difference, but some difference within the computational domain and then the boundary node. So that's the distinction, either being solved by the CFD solver or being imposed by the boundary conditions. So what are the appropriate boundary conditions for this flow? Let's have a look. Just to remind you of this explicit predictor corrector method, the ij's are the spatial differences and at time step n, and then we have the same indices for the momentum. So this is our 2 state variables, our density and momentum. All right, let's look at each one of these in turn. So At the left wall, at x is equal to 0, we're going to apply no-slip boundary condition. So in the predictor corrector sense, the left wall, right, has got a node there and a node here and a node here. And so in a sense, this is the I node, this is the I plus 1, this is the I plus 2. So when you look at this stencil for the half step, you're drawing information from the I plus 1, I plus 2, I plus 1, and the I nodes. And then in the full step, you're using both the old time step and the half time step. You're going to divide by 2 essentially, so you're going to take the average of those two. And you're still drawing information from 2 nodes away, meaning it's still second order accurate. So that's for the density. These numbers here come from the Taylor series expansion of this and the manipulation of the stencil itself. But essentially, you can see that it's drawing information from 2 nodes away. The momentum is simple because u and v are 0 on the boundaries, you just force that 0 boundary condition, and you're still allowing rho to vary on the boundaries. All right, so the density of the wall can fluctuate. There's no y dependency in this stencil, that's a good point, because there is no y gradient along the wall that feeds into that node. And then the stencil reaches out 2 nodes in a forward difference to retain central difference. The same is pretty much true for the right-hand boundary. On the right-hand side, you've got a node, and then you've got 2 nodes. So you've got the I minus 2, the I minus 1, and the I node. So you can see that's where they appear, I minus 2, I minus 1, I for the predictor step, and then the corrector step is the average plus the correction. And then the same is true here for enforcing the no-slip boundary condition. And again, there's no gradient in the rho u direction, so in the y, that should be, no, in that y direction, right? Here, it's very similar along the bottom. We've got a j and a j plus 1 and a j plus 2, and we're drawing information. Those should be j's. And then we're forcing the no-slip boundary condition. So that all makes sense. And then at the top where we impose the boundary condition, we're going to do the same thing, except we've got an additional term here. So we do have gradients both in the x and y direction here. So we're going to include both of those gradients in the I plus 1, I minus 1. So that is our central difference there. And then reaching down into the j direction 2 nodes. And we do that both in the predictor and the corrector step. So that makes a lot of sense as to what our boundary conditions are. And these are listed in that handout. All right, so first thing to do is to set it up and converge the mesh, so to speak. So this is for a Reynolds number of 400. So here's a simulation. It's a 10 by 10 mesh, so you can see it's going from 1 to 11 because it's 0 relative, and this is Matlab, and it won't plot zeros. It won't have indices of zeros. This is 1,000 iterations, and it took 7 seconds for such a small domain on my Mac laptop. 7 seconds, so that's not bad at all. And you can see that it has the basic shape. These streamlines here, this flat bit, is a result of the plate itself over one node from 10 to 11. And then it induces this beautiful recirculation here. Now these were plotted in Matlab using a stream function that I'll show you. All right, so that's the plate. Now I increased the resolution from 64 to 64, and lo and behold, we've got some new features. First off, it took 2 minutes, almost 3 minutes to do the same 100,000 iterations. And you can see we now have our secondary flow appear, so that's pretty cool. Now I went ahead and did 256 by 256. It looks pretty much the same. You know, discount the shading and the coloring and try to focus on the shape of these streamlines. And the streamline shape looks pretty pretty much the same, as does, say, big features like the center of this. And you can see that the center of, whoops, definitely looks, boy, that was an unfortunate slip. Definitely looks low there. Looks like it's around, the center looks like it's about there for the 10 by 10. But the penalty is that took an hour and 16 minutes. So you don't want to develop your codes at high resolution, right? You want to develop them at low resolution, and then once they're running, you can gradually increase the resolution, right? Don't be that person that turns the resolution up all the way in the beginning. All right, so this secondary flow is really a path towards turbulence. That's why we're excited about it. This primary flow induces a secondary flow, and one can imagine that it continues to happen. More and more secondary flows appear, smaller and smaller eddies, and eventually you've got yourself a fully turbulent flow. And if you want to see a nice video on that, the National Committee on Fluid Mechanics has a video, of course, specifically looking at secondary flow, so be sure to Google that. And then just for your own information, how I generated these plots is using this stream function, this combination of stream slice using the data dump for the U and the V with no arrows in the cubic fit. And then you actually plot them here. So this will generate the vertical and the RVert data, which will then be plotted by Streamlines. So try that out. It's a pretty neat function. It gives you some really beautiful plots. All right, so we converge the mesh, right? And in order to really do it, that was we just kind of looked at it there. And a nicer way to do it is maybe to take a cross-section. So here's the domain here, and that red line represents a cross-section across the domain. I'm going to plot the velocity profile there. So for the 10 by 10 mesh, it looks something like this. Boy, I guess I should have labeled these axes. This is the U velocity, and this is the y direction, the dimensionless y. So this is actually y over d. And this being non-dimensional, you can see that we're hitting 1 right away there at 1. So that's our boundary condition. And then you would imagine that it would decay and it would go through 0, and we'd have some negative part because, right, it's flowing like this and then around like that, so one would assume you would get both positive and negative. But in this particular case, for the low resolution, in the center, I'm plotting this line there around 5, so we don't really skewer the center of that too much. But when I increase the resolution, I get quite a different solution, right? Not only did the secondary flow appear, but you can see that we're getting much more negative numbers for the lower portion of the flow, which makes a lot of sense. And then if I increase the resolution a bit more to the 256, you can see that it's different for sure. And so if I were being paid to do this simulation, I might try a little bit higher resolution to make sure I completely resolve this. But it's all about what you're trying to do, right? All right. We can also converge this solution in time. So what we just did is called a mesh convergence, and then we should also look at it in time. So we're going to calculate something called the residual. And the residual is really anything that allows you to characterize the overall converged nature of the domain. So I'm going to pick density, and I'm going to take the difference between one time step and the other time step. And I'll take that difference at every node and then sum that up over the whole domain. So you would think that would go to 0 in the steady state, but it never does. It's because it'll flip back and forth between the solutions. It'll reach a converged solution where it's changing the density back and forth across the time step. So here's what it looks like if I plot iteration numbers. So this is my 100,000 iterations, and it converges, quote, quote, so quickly that you can't see it. In fact, it converges to a non-zero number, and if you look at it, it actually is increasing. It should go to 0, but it's slightly increasing. So for such a small mesh to take so many time steps, that's really unfair to have a 100 nodes take 100,000 time steps, we're beginning to accumulate round-off errors. So the solution is wandering just slightly as we take all these time steps. If I increase the mesh resolution to 64 by 64, then you can see some temporal variation within the residual as it converges. It pretty much converges onto the same thing. It doesn't do that wandering there, so it's a flatter line out towards infinity. But as the resolution increases, the time step decreases, and it takes it longer for it to converge to the solution. So in this case, I might want to take 25,000 iterations or 30,000 iterations. And in the 10 by 10, it looks like it was done at 1,000. That was the first data dump I did, was at 1,000 iterations. Here's the 256 by 256, and how many iterations would you say you would need to converge that mesh? Maybe something like that, right? Maybe 90,000 iterations. So if you look at the required computational domain size here versus the time it took for it to run, right? Time is money here. So this is, each one of these was 100,000 time steps, but the domain that only had 100 took 7 seconds. The domain that had 64 by 64, so closer to 10,000, took about 100 seconds. And then this 256 by 256 took over an hour. So it's not quite linear scaling. It actually looks like it's going to increase kind of, a lot as the computational domain, as the number of nodes goes up. My penalty that I pay is how long it takes to run this simulation. So really, when we converge the mesh and we converge the time, we're kind of trying to find a sweet spot for whatever resource we have available to us to do this computation, and what our tolerance for pain is. There was a great article that I read once that said that we can only wait about 15 minutes for a solution, and I find that to be the case. It's hard to just sit there and stare at the screen going through iterations. All right. Keep in mind, this is a time-accurate solution, right? Unlike that Laplace solution that we did earlier. So when I plot a movie like this, which is showing the vectors, and I'm only plotting every 10th vector for the 64 by 64, you can see that this solution that we get is the time-accurate solution. It does have meaning because we are keeping that time step accurate with the Courant stability criteria. So let me play that again, and you can see this start up. So you can see it start up, you can see the vortex initially form, and then it kind of migrates into the cavity a bit. And then if we watch it, we would say, well, it's come to, it looks like it's complete around 17 or 15, but in fact that residual plot that I showed you on the previous slide shows that it takes almost 30,000 for the residual to kind of calm down. All right, and if you wanted to know, I made this movie using Linux command. This is a one-liner in Linux. This is why you gotta love Linux. It's this ffmpeg command, and it says give me 12 frames per second using a pattern, input files for every PNG file in the directory, create me a movie AVI. So you don't have to buy software to do this stuff, right? You just download it for free and run it on a Linux or Linux emulator window. All right, let's look at another movie. This is a movie where I didn't skip every 10th frame. So this is all 64 arrows, and you can see a little bit better how this thing behaves. And this is Octave that did this. And this is using the quiver plot. And I'm going to include that in the zip file that I include for this cavity solution, but you can see that it forms something that you can visually see where the vector is, they are, but you can't really see this region too well. So I'm going to zoom in and we'll look at that region by itself. That region corresponds to the secondary flow that we saw. And so we're down here in the corner now, 0.8 to 1, 0 to 0.2, so it's a 0.2 by 2, and you can see the arrows form, and then you can see they actually spin in the opposite direction. So here's our little recirculation region that comes about by 30,000 iterations. All right. So here's the solution in Kundu's book for this problem that describes this. This is for the Reynolds number of 100, and this is for the Reynolds number of 400, right? There's two separate solutions here, so you can see that it looks like the secondary flow is less pronounced for the smaller Reynolds number. And then here's my solution, just laying it on there so we can convince ourselves of how cool it looks. There's just another plot of it. So it looks like we did a pretty good job capturing that, or at least Kundu did a good job when he did this calculation. And then another way to assess this is to, again, look at a slice through that domain. So this is what's published in Kundu's book for the 100, 400 Reynolds number. Here's the profile for the 400 in the dark line, and then this combination dashed gray line is the 100. And then if I lay my solution on top of it, it looks pretty good. It looks like it maybe needs a little bit more time to iterate here instead of the 25,000 iterations, because remember, the information is moving really through the domain like this as that plate drives the flow down. All right, so what we're going to do next is talk about the square cylinder project. And so in this project, you can take that cavity code and you can convert it to solve this problem. It's flow over a square cylinder, and we have an inlet flow of u, and then both boundaries are moving at u. And this will just allow us to have a smaller domain rather than having a free stream infinite domain or a stationary wall. This will converge faster. So you've got your 4 boundary conditions, and you're going to have to impose a boundary condition on this square as well, right? A no slip. So you've got both no slip and free stream and an exit boundary condition as well here. So you'll have to come up with all of those. When I did this, I used about 150 by 30 initially because this is supposed to be, I think, 1D here and the distance here is 1D. So you slice this up into 3 equal parts, and so that's why I had J of 30. So I had 10 nodes across here, 10 nodes there, and 10 nodes there. At least that's what the instructions were in the book handout that I gave you. All right, so for a Reynolds number of 20, you get this kind of flow where you get this beautiful smooth streamlines and the recirculation region like this. And here's an image showing a right circular cylinder with the closed circulation bubbles around it. And then as the Reynolds number increases, you'd get something like this. So this is my solution where I ran this, and you can see those beautiful vortices at the higher Reynolds number. You can see a little bit of disturbance when the solution starts up, like when it clicks over at 100,000. You can see some noise and things in the beginning over here, and then it straightens itself out, and you get the von Karman vortex street that you're used to seeing. You can see it takes just a little bit to get it going. And these are contour plots, right? These are contour plots done in Octave, and since they're contour plots, you're getting circles of a similar velocity, right? So that's kind of why you even see those vortices, is that they're contoured and not streamlines. So Octave right now doesn't have a streamline function. So, but the contours actually, I think, are better than the streamlines. All right, so this was a little bit bigger calculation. It took 5 minutes, not very long to run this at all, really, once you get it going. And one could ask, why do these vortexes start in the first place? It is this path to turbulence, right? It is this those stationary vortices become unstable and get washed downstream. All right, and just if you want to know how I made the movie, once I created these plots, I cropped them all using this one command. You can crop every file in the directory. That's beautiful, using the pixel definition. So this is the window size for the crop, and this is where in pixels you place that window. It's just beautiful, right? And then here's how we make the movie. So in 2 lines, you can do what some ridiculous code that you might buy would take you 5 hours to do. All right, here's the streamline. So this is a Matlab. This is using the streamline functionality within Matlab. So some initial startup, and then once it gets going, you can see these streamlines. And maybe I should have run this a little slower. This is 12 frames per second. It's kind of flipping fast. All right. So what about some global measures? Like, here's what this is drag coefficient over time. So of course you would expect it to not, this is for the Reynolds number of 20 up here, and this is for the Reynolds number of, what is this, 100? Yeah. So here you would expect some initial startup, and then it would eventually smooth out and become kind of constant at a Reynolds, and then you get a constant drag coefficient. But when you've got this vortex shedding, you would have some initial instability, which he's not showing. See, he's already at 54 seconds. And then it would come to some beautiful steady state as it fluctuates as every vortice is being shed. So this is the shedding period here. And then this is part of the mesh convergence, looking at grid spacing resolution versus how the drag coefficient changes. So it's important to do these things if you're going to try to pull out real meaningful data. All right, well, that's the end of this lecture. I hope this gives you a good idea of what we're trying to do with cavity-driven flow, and we'll talk to you later.